Okay, welcome back, everybody. Yeah, so it's a pleasure to you know, it's University High School. We'll see how the full chat. Okay, thank you for the introduction and for the opportunity to speak on my work. So, the talk will be based on joint works with Campana Rousseau and another one recent work with Campana Rousseau and so first I will maybe emphasize some notions that already appeared of general and special type, and link them with hyperbolic properties of varieties. So for the talk, X will be smooth projective over C, and dimension n. And so we will try to relate the irrational geometry of X and the behavior of what we call entire curves. So an entire curve is just a holomorphic map from C to X that is non-constant, because our goal is to study the distribution of such curves. So if we keep the constant, then we cannot see anything. And we will study some hyperbolic properties that already appeared, and that we can put in a chain of implications. So first, X is hyperbolic if any holomorphic map from C to X is a constant. So I will just write there is no entire curve from C to X. Then it will be weakly hyperbolic. I think it was introduced as pseudo weakly hyperbolic. So there's a lot of different names right now. So weakly hyperbolic if there exists a proper severity of X such that any entire curve, I will not say again that it is a non-constant, any entire curve has its image contained in Z. So this is a strong algebraic degeneracy of entire curves, in the sense that we not only ask that F is not dense, but that if we take the closure of the curves, we still get proper severity. And so there is, of course, hyperbolic implies weakly hyperbolic, and it also implies that there is no dense entire curve. And now we will relate these different versions with positivity properties of the cotangent bundle. So the guiding idea is that the positivity of the cotangent bundle should control the geometry of the curves, and precisely. So we have the conjecture that is only known for curves. That hyperbolic should mean that all subvarieties of space are general type. And we will see later that this also means that X doesn't contain a subvariety of special type. So I will come to this undefined special type soon. Then weakly hyperbolic by this conjecture of Greenberg and Long should be X of general type. And then you see that if this would be true, we cover at least this implication, because instead you are degenerate in a proper sobriety, it is a general type, and then you can iterate the reasoning until you get only constants. So this gets well in the picture. And here, so there is a notion of special type, and this should just be that the X is not a special type. So for curves, there is no gap between general type and not a special type. But in general, we will see that there is some intermediate situations, non-pure situations. Okay, so this is a conjectural picture, and I should recall or introduce what is the general type and special type. So X for general type is 1. So I have put this in this way. So dimension of H0 of X and Kx and to the N will grow like M to the N. So this is the maximal exponent, maximal growth, and this corresponds to the determinant of omega x, n dimension. And then X of special type, it will be defined as the opposite of the situation in a strong sense. We will take not only the top external power, but all external powers. And then, since we don't have any more alignment bundles, we will take rank 1 subsheets. And we will ask that it has never a maximal growth by, I think, a work of Bogomolov. This means that this growth is smaller than m to the p, where p is the exponent of the external power in which L is. So you can see that these properties are opposite. So here is not maximum. But for every external power. And so there is morally, so this L with maximal growth is called Bogomolov sheaf. And morally, Bogomolov sheaves, they are associated to varieties of general type over which when you have the dominant map from X to this variety of general type. So the idea morally is that this L, they should be obtained from the canonical bundles of varieties of general type when you get surjective map. So morally, the idea of the definition of special that you have seen this notion a little weakly special is that X cannot dominate the variety of general type. X cannot dominate the variety of general type. And the idea is that M is obtained from the pullback of some AC with the crazy. So, but actually, this moral thing can be made precise by introduce Orbifold-based vibration. So this is done. All of this first part is done by Compana. Is the work of Compana. So, make the slides. So if you have a vibration from X to D, you will define what is the orbifold phase. So the idea is to encode all multiple fibers of F and to use them to increase the positivity. Okay, so actually, sometimes the variety Z itself will not be of general type, but if you increase the positivity of the canonical line bundle by encoding the positivity of multiple fibers, it will become of general type. And then you get that X is of special type, even if there is no orbifold morphism to a variety of general type. So this is what I will explain. So you take delta F, it is the sum over the divisor D of 1 minus 1 over mi di, and this is orbifold coefficient, the little ramification. And mi is called orbifold multiplicity. And there is at least two ways of defining mi. So one probably you are used to is with divisible multiplicity. The one of Compana is different, is with the maximum. So I will explain this. So mi, you take the pullback of di and you write it as the sum of mij dij plus an exceptional part, which will not surject on di. And then mi, it is the max of the sum, the max of the mij. So in particular, it will not sorry. In particular, it will not divide the whole energy. So it is not like what you would do in space. So in general, this is a market. So why that? It's because if you, as an example, you look at the curve from C X, and then you look at your vibration. As an example, you see that if you have a fiber like that, with a prime multiplicity, the composite match will still ramify at order at least 2.
I think you mean GCD, maybe.
Yes, I'm French. I'm not used to English notation. GCD and GCD, I'm sorry. I always do mistake. Thank you. And so it would be somehow a waste to put 1 here, because you have some positivity that you can take into account, which is a little moral. So, and then what we also show that it is the good definition in this context is the rents obtained by Campana. So, okay. So there is a first theorem of Campana that X is of a special type, if and only if there is no Orbifold to a variety of general into surjectivity. Variety. I don't know English, but the variety of general Orbifold general. So, for this example, we notice that only the KZ is of general type, maybe it's not. KZ plus delta P will be. Okay, and then this is somehow decided that X does not dominate any variety of the general type. Is the basic argument. The proof of what is called the core theorem. You have to do more than this, of course. But you can see a little T. So the core theorem says that also with Campana says that it's more general, but we will stay in the context of projective smooth. And there exists a unique up to birational equivalence vibration from X to Cx, which is called the core of X, that splits X in quantitative parts, in pure parts, in pure quantitative parts. So first, the fiber, the general fiber is special. And the orbifold place is of general type. So this doesn't work if you try to work with the GCD, you will not get enough positivity. So if you want to have a base of general type, you have to be what called multiple fibers with the So this is a good result of irrational geometry. And now somehow it allows to extend the Green-Griffiths-Long conjecture from varieties of general type to arbitrary varieties. Or maybe I wanted to say something first. That the dimension of X is the dimension of Cx, means that X is of general type. And the dimension of Cx is 0, means that X is of special type. But you see, if the dimension is more than 2, at least 2, you have also non-pure curve. So for curves, you have dichotomy, but in higher dimensions, it's not pure in general. So here the idea, the basic idea, it's more complicated, is that if X is special, it's over. You take the vibration to a point. And if X is not special, you can find a variety of general type and the vibration to it. And then you want to apply this result to the fiber. So you have to be careful, it's a bit more difficult. But you want to extract all positivity until you reach a special type. This is the moral idea. Okay. So yes, so now we want to extend the Green-Buffet conjecture arbitrary x. So we take x like that, and then we take the core map. And this is we can look at the composite. And what would be right if we believe Green-Buffet conjecture? It's simply this is not general time. That we have here algebraic degeneracy, strong algebraic degeneracy. And what I want to say, yes. And what kind of curves are these? So these are not arbitrary curves from C to Tx, these are composite. So here they have so this composite have to satisfy some ramification property. Ramify at order at least ni along vi. So this in this context, if we put here delta, I forgot to recall, but 1 over 1 minus 1 over mi di. So this will be what we call the Orbifold curves in this pair. Orbifold entire curves. From C to Cx delta. And what is interesting, I think, is that these curves are exactly the curves that are studied in Leuven theory, where you want to quantify how close entire curves are from divisors. So this is somehow standard object of study. Standard object studied in Leuven theory. So you can translate a lot of result of Leuven theory in the language of Campana. And so the conjecture of Campana, one of the conjecture of Campana that I mentioned instead of taking it in the conjecture is what is that the special subvarieties they are exactly the Zariski closure of entire curves of standard of X. Sorry, they are the Zariski closure of image of entire curves. And so what is the generalized Green-Buffet conjecture? So maybe I insist that here we want to treat arbitrary ordinary projective varieties, and we are made to use Orbifolds. So somehow it's not a technical complication that we have to make in papers. It's really something that comes into picture when you study standard not in the Orbifold category, but compact. So what is the generalized conjecture? So for all X, there would be a strict subvariety of the core, such that for all F from C to S without verification conditions. Either f of c is in the fiber of the core, or f of c project in Z. It's included in the pullback of C. And so, furthermore, moreover, Z should be, so the exceptional locus should be the union of special singularities of Cx. This is the okay. So somehow, sometimes you will not get. So if you believe in this, if X is not special, you will not admit that entire curve, but you will still be covered by the entire curve because they are the fibers of the core. Okay. So here we don't have a strong degeneracy property, but just a known. I think this explains the things that I arrived relating the chain of implications in those topics. So maybe I have to very little. So
yes, give some example of X in CX or some integration.
Not freedom. So you take a variety that is special, not freedom. I would have taken a product of the special
What is there some example from this channel type?
Probably there's a lot of examples, but I'm not very good in them. Maybe it's very here, but okay. So somehow this, okay, I have to be honest, this part of the motivation. Now we will only study, I will not study the core map, I will just study the base. Okay. So, okay, so maybe I can give example of hypersurfaces in PN, where some of these conjectures are known. So you have this work of Clémence, Ayvoisin, and Pachenza. Will tell you that if you take H very general, with degree, so with T more than dn, and then you have a list, which is so E1 is 4, then you have 2n plus 1. And then you have 2n. Then it is 5, and then you don't have your all subvarieties are on the general type. So this should imply hyperbolicity, if we believe in the conjecture. And then on the hyperbolicity side, we are very far from distance. Actually, yes. So first, maybe this result of Divergio Mercuruzzo. and that was improved by Bertie. And then myself, I filled some gaps and I did the logarithmic case. They say that you have the strong algebraic degeneracy. For general hypersurface. So each time each time I say general to answer a question that I gave earlier, there is no precise understanding of the bad locus. We just know that it is true on 10 certain subsets of the parameter space, but there is no geometric information on the boundary. So here's progress rate degeneracy for general vector surfaces of a very large degree. And then you have the hyperbolicity. So this is the weak hyperbolicity. And then you have the hyperbolicity, so it's a result of Protek. And then the Mali did another proof through the strategy. And recently, Riedel and Young gave an alternative in the problem tool. It says that you have hyperbolicity for general hypersurface of a very large degree, even larger. Yeah, a little larger. So in Riedel-Young, they take the explicit bond that you have here, and they replace n by 2n in the bond. So it's the same kind of very large bond. So all of the proofs here, they use what we call jet differentials, and that's what we introduced by Green and Griffiths. So I will try to say something on it. To give you some idea of the proof. The differentials, they are algebraic differential operators with polymorphic coefficients. And the ID, from Green and Griffiths, and maybe before, is that to study, to get algebraic degeneracy, you first study algebraic degeneracy at the level of jets. And then you try to make some elimination or to use some argument to get the algebraic degeneracy of the curve itself. So I have to say that this is really challenging. So if you have X, you have the jet bundle above it, and the coordinates are the coefficients of the Taylor extension of order K. So this fiber is very large. So what you will first get is a proportional variety at the level of jets, where all jet occurs at the length. And now you want to explain why the image in the base is still proportional variety. And here somehow there is no hope from the dimensional point of view. But so in the case of hypersurfaces of projective space, there is a strategy of Q. And I will be a bit sloppy. So you consider, so this is also an idea that is present in the work of Voisin. So you consider the hypersurfaces in family. And so the parameter space is a projective space, which tangent space has a lot of positivity. And this will allow you to differentiate along the universal family, to differentiate with respect to the jet coordinates. And somehow you will be able to do, I would say, a Taylor formula. So, you know, if you have a polynomial and you want a coefficient of the polynomial, if you have a differentiation, you just have to apply the Taylor formula and you get the coefficient. So this is the same idea. You will differentiate with respect to local order vector fields, and in the end, you will get something that still vanish. Okay, so this is a sloppy idea. But it's really the idea, I think. So this is so the point now is first to obtain algebraic degeneracy at the level of jets, and then using this idea, you will be able to obtain weak hypervelocity. Okay. So this is the approach of the Darondeau method. So what are the so maybe I should have done it before. The jet differentials of order K. Okay. And we explain. There are the polynomials in jet coordinates. For the K that are homogeneous for the reparametrization at the top. With I will write like that. Sum of A I T prime I1 etc. And if you make the weighted this is our multi-index, and if you do the weighted sum, so this is the number of primes, it will be n. And this is the holomorphic. Okay, and so this is a local picture, but you can make a bundle, which is called the Winquist jet bundle. And then this bundle from this description, maybe you see that you can get a weighted bundle. So there is a multi-filtration. This is the green office. There is a multi-filtration. There is a weight by the weight of highest derivatives. Which graded bundle. So So integrated bundle, somehow you will consider zk up to polynomials in zk minus 1 z prime. So when you make the chain rule, it will behave like z prime. So this is heuristic. Yes, this is a heuristic. If you look at the derivative of parameterization at the goal, this is actually just p prime times base derivative of f plus lower order terms. And you see that this does not depend on k. So this is to say that derivatives that have lower order terms, they behave like first derivatives. And so this gives you the idea of the graded bundle. So you will get the tensor product of symmetric powers. And here's the weight. So these are the case order derivatives. This is the first. So the weight will be 1 times L1 plus k times Lk is n. Exactly much. So this will be important if I have time to go to Orbifold system. And an observation. Sorry. So the question is how to produce. So first we have a vanishing theorem. Due to the Blanquet-Fils de Mali, that if you have a jet differential vanishing on an ample divisor, and you have an entire curve, then the corresponding differential algebraic equation is satisfied by f. So this is algebraic degeneracy at the level of jets. And so now so you have two ingredients, and we just need to produce a jet differential vanishing on a divisor to be able to finish the strategy. And so here, to produce jet differentials, actually there is the strategy of Demali is to use Morse inequalities. And they give a lower bound to any truncated Euler characteristic, and in particular for H0 minus H1. And what was pointed out by Cadorel, that was implicit in the mail's work, is that when you consider a graded bundle, the H0 is in the wrong direction, the inequality is like that. But if you are able to consider H0 minus H1, it's in the good direction. So the H0 minus H1 of the Kn, it is larger than the one of this of the graded bundle. This is a general fact. And this is larger than the smaller than H0. So actually, you can work with the graded. And it's much easier because here you have only order 1 data. You have only cotangent. so you can do your work. And so the idea is a problem next step to the right. Which is, I think, the only optimal result beside using a general factor solution. So X is the general type. Then you have jet differentials vanishing on a local divisor of large degree. And so you have algebraic degeneracy at the level of jets for K large depending on X. So this is the optimal result. And then, as I said, in the general case, you need a strategy to eliminate, which is totally not known. Right? Okay, so I think fit a bit in rush, I think. I will not write, so the strategy of Leuven to get hyperbolicity is to use the result of Differentials, and they observed that so the base locus of the jet differentials they behave well with respect to hypercompensations. And doing some using some incidence relations, they were able to get the hyperbolicity by increasing the codimension of the yeah. So it's a bit sorry, I'm not excited. I don't want to spend too much time. So the idea is really to use Leuven Rousseau plus some hypercompensations. But for complex proof is quite different. Actually, it proves non-pairless property, which is so maybe here I didn't say. I'm sorry. For case one, this is just the symmetric power of omega x of symmetric differentials. And you know that if this has a lot of sections, and if omega x is ample, then you can get hyperbolicity. And somehow this will never happen for hypersurfaces in the end because you need to have order of least equal to dimension to get sections. But Damian is able to prove an non-correlate property which is analog of ample potential bundle, and then he proves hyperbolicity like that. So it's a little different story. But also it's a very stronger property what he shows. Okay, but you can use openness of openness. Okay. Okay. So now, when did I start? Sorry.
Maybe just a few minutes after the hour.
Okay, so it's, I have to get time. So now we're going to speak a little about the Orbifold project. And to show you what we can do, but also what we have no hope to do. So, okay, so now I take x before and then delta, where delta is the sum of 1 minus 1 over mi pi. And this time I will explain why we are left to this. Mi, it will be in Q, larger than 1. And it can also be infinite. So the infinite ramification, it will correspond to the open case where you have to avoid the divisor. Okay. And so the curves f x delta they have to ramify at order by definition. They have to ramify at order at least, but not a multiple mi. And if mi is infinite, they have to avoid. Yeah. So when all the mi are plus infinity, this is just the usual. Here I ask that the support is the SLT. And so this is the usual smooth logarithmic case. And the integer coefficients they correspond to the only to the logarithmic device. Okay, and blah, 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 blah. So as I said, you can study this curve with the linear theory. With I would say pure linear theory, because we use linear theory in some other approach, or you can try to use alternative approach of jets, differentials. And actually, they don't cover the same cases. So, as an example of linear theory, you have this carton second line theorem. So if you take a union of hyperplanes in Pn, and you ask that the sum of 1 minus n over mi is pretty larger than n plus 1. And here, if mi is smaller than n, you don't want to consider. So you take like that. And then you get algebraic degeneracy. And so you see that in this case, you cannot see the multiplicities that are smaller than the dimension. So, and in your case, so we will go to the standard approach. So first, we need to define the cotangent bundle. This is what done for local value component. So what you do, so you take an adapted cover. So this means that it ramifies at order a multiple of mi over di. And somewhere else, we don't care. And then you can look at the. So normally the cotangent bundle it would be a subsheet of the logarithmic cotangent bundle. But to make it fine, we need to introduce roots of the variables. That's why we take this adapted cover, and then you take the pullback of the cotangent bundle, and you look at the restricted sequence. But here, instead of taking the pullback of the di's, you can divide them by mi. And so the sheaf defined by this vanishing is what we call the Orbifold cotangent bundle. So morally, here, we have the di over di, And here we get a vanishing WI, where WI and I is here. So this is what Kapala he writes of some dz over z 1 minus 1 over n. So this is the coefficient of the delta. Okay. So what you can prove is that actually another way to define the orbital protogen bundle is to say that these are the logarithmic forms. There are the logarithmic forms that still act holomorphically on the curve. If you repeat them as operators, I'm just saying that if W is this, omega is this, and you take F is Z alpha, then what you will get is so then that exponent is positive. If alpha is not equal to F. Okay, that's not the multiple what I want, this is ID. So this is what we will need for higher order differentials. But actually, this stupid little computation, it will introduce the main difficulty that we will face. So now we take Orbifold differentials. You say that you take the subsheaf of the logarithmic jet differential bundle. And that take the fact of sections, that fact holomorphically on orbifold entire curves. So you don't have such a nice sequence in this case. It's more complicated, but we can look at what it is. So I will just take a simplified position. So okay, so here now the question I will change is what vanishing shall we put here? So I take again F is the alpha, and I put it here. And of course, the only difference is now I have minus pi. So d alpha beta minus pi. And I want this to be positive if and only if alpha is larger than n. So what I will take is beta. Is pi over n. Okay, this is easy. So this shows you what you have to take in the local coordinate. So you have to take the diz d but over z. So this is the logarithmic jet coordinate. But then what you have to put here is z pi over m. But this doesn't make sense, of course, if because here I identified if I is larger than n. So this is the idea, but actually you will put 1 minus I over n plus. Okay, so what I try to explain is that if I is larger than n, then you don't see anymore the tangent t. Okay? If you have a contact over m and you differentiate more than n times, you don't see anything. Okay? So this is why there is this additive complication that you have like plus. So these are the jet coordinates. And the idea is really to mimic what we did for the tangent bundle. But one
It should be finished in 30 seconds.
30 seconds?
30 seconds.
Wow. Okay. So one consequence is that the graded bundle now is not as before the sum of symmetric powers, because you have to change the orbifold multiplicities. And so here you get the new pairs that you have written like that. Okay, better. And you see, as soon as J is larger than all multiplicities, you will get nothing. At infinity, you will just get the sum for mi is 1 of the GI, so the logarithmic part. So you will lose all additive positivity that you had put in the orbifold divisor. And this is very bad because so each factor loses positivity until you reach logarithmic. And for interesting applications, we don't want logarithmic cotangent bundle to be positive, otherwise we don't need orbifold. We use it already. So now this is the main problem. And for instance, the domain theorem is really asymptotic. And so you will not be able to use it here. I don't have time. I can give 2 or maybe 3. So first illustration is so the problem is like for surfaces. I will just say this first, is that for surfaces, if so in the interesting case, this is not positive, Euler characteristic becomes negative. It becomes negative. So you have that the H1 is larger than the H0 and the H2. So you are not able to use chi, or it's the same for the truncated you just provide the H. So in the orbifold case, the H1 will become very big and high everything. So this is the main problem. And so 2 examples. If you take P2 and you take H of arbitrary large degree, then you put multiplicity 1/2. So in this case, there is no jet differentials at all. Even if we don't ask to vanish on our divisor, so nothing. So you have no hope to use Fourier series arguments or anything like in the former bad case. Here you have nothing to start with. So jet differentials say nothing about this example, whereas the orbifold canonical bundle is as large as you want. You can take any degree. So this is maybe the first pathological case. We have also the case of abelian varieties, where this time you have just differentials, but if you ask for bigness, you will never get it. When you take a smooth boundary and multiplicity smaller than the dimension. And maybe I will finish by the positive result. We are still able to do something.
Well, we should be stopping pretty here, but yeah, go ahead.
Okay, so we are okay. So just to say that we are able to cover some cases that are not covered by like P2, and I think 11 lines with multiplicity 2, and we can show hyperbolicity. And recently with the MILI, we have shown that we are able to produce differentials, but we have to take K is equal to dimension. So we can still do something. Sorry for bad time. Yeah.